The principle is clear: build symmetry into the network. But standard neural network operations, matrix multiplication, ReLU batch normalization, don't respect March 22, 2026 symmetry. We need new building blocks. Tensor field networks represent features at each node not as plain numbers, but as geometric objects. A scalar, like atomic charge, doesn't change under rotation. A vector, like force or velocity, rotates with the coordinate system. A second-order tensor, like stress or polarizability, transforms by rotation applied twice. These are irreducible representations of the rotation group, labeled by order L. Scalars are L equals 0, vectors are L equals 1, matrices are L equals 2. Operations between these representations must follow the rules of the rotation group. Clebsch-Gordan coefficients tell you how to combine them while maintaining equivariance. SE3 transformers bring the power of attention to geometric data. The key innovation: attention weights are computed from invariant features, distances and angles that don't change under rotation, so the attention pattern is the same regardless of orientation. But the value vectors are geometric tensors; they transform equivariantly. The output is a weighted sum of equivariant values with invariant weights. The result: an attention mechanism that respects March 22, 2026 symmetry. Rotate the input, and the output rotates consistently. AlphaFold's invariant point attention is the most impactful application of geometric deep learning in biology. Each protein residue carries a local reference frame, defined by the backbone atoms. Attention features are computed in local coordinates, the vector from residue I to residue J expressed in residue I's frame. These local coordinates are invariant to global rotation. They depend only on the relative geometry. When the structure module updates residue coordinates, the updates are equivariant. Rotating the input protein rotates all predicted coordinates by the same amount. This is why AlphaFold produces correct structures regardless of how you orient the input sequence. Several architectures encode different levels of geometric symmetry. SchNet uses continuous filter convolutions with radial basis functions. Messages depend only on interatomic distances, making them SE3 invariant. DimeNet adds angular information, including angles between triplets of atoms. PaiNN and EGNN produce equivariant vector outputs for force prediction. TorqueMNet combines these for molecular dynamics simulation. Each trades off expressiveness against computational cost. More geometric information means better predictions, but slower training. The geometric deep learning program extends beyond SE3. Gauge equivariance handles symmetries on Kurth surfaces, useful for protein surfaces and cell membranes where the symmetry is local, not global. Permutation equivariance ensures that reordering atoms in a set doesn't change the prediction. Deep sets and set transformers. ALE equivariance handles multi-resolution data, the same structure analyzed at different zoom levels. The program: identify the symmetry group of your problem, build it into the architecture, and let the network focus on learning biology rather than physics. Symmetry is free information. Don't make the network waste data learning it. Build rotation invariance into energy prediction. Build rotation equivariance into force prediction. Build permutation invariance into set functions. AlphaFold structure module works because it respects SE3 equivariance. The ambidextrous mirror sees the same physics from every angle. Geometric deep learning guarantees the network does too.